Hello, Diamonds in the Rough. So, welcome to the third season of the AI series. And in this one, we're going to learn about logistic regression, or you can say classification. Previously, second season, we learned about linear regression. Let me mansplain few things. So, actually, this could be the part of second season only, but I thought over here the difficulty increases exponentially. I have tried my best to keep it as simple as possible till now, and over here we're gonna go like in the scale of difficulty, we're gonna jump a little hoop, and it's not that difficult, but you might find like the things little faster what we have done, but you don't have to worry. There are so many other courses which are even faster than that, so you'll probably feel much all right. And if you even if you don't get the answer, or you get stuck somewhere, that's fine, believe me, because when I was studying this, I didn't understood in the first go. I had to take the Andrew course like 3 times back then, and I'm betting sure it will be better. Although he's my mentor, but still this one gonna be little better than what he has taught, and and much simpler, I would say. And it took me time, so probably you might also get stuck with this. So just we have to be patient, and you don't have to quit. And just, even though when I have learned it, when I applied in my work, and when I came back for teaching, then I have understood a lot of things what I been teaching today. So for me, even though when I also became a ML engineer, that time few of the concepts was not very clear, right? It was like 70%, 60%, 80%. And when I came back for teaching, it became 90%, right? 99 or something. So whenever I go and I teach, something new will always see. People tend to miss out while explaining things. So I'll make sure that thing is in this video. And if you get stuck, just make sure that the best of us are stuck over here, and it's fine. And when you will get stuck, just screenshot it, try to expand it with the equation or ChatGPT or something, so that will help you. So not wasting much further time, let's get started. So basically, we will start with our data. As you have seen, we will have like this simple data points which you used to use previously as well for linear regression. This time we will use it for classification. And what is different this time is that the y labels have only two classes, like basically two numbers, 0 or 1. 0 belongs to one class, the one class, and the 1 will be to belongs to the class. So we can categorize our data into two groups. One will be 0 group and the first group. And same we will have x1, x2 feature. So first step is, whatever do we have to create a predict function. Not predict function, yeah, you can say we have to create a predict function, and then we have to plot this data and see how the data looks like. So when we plot, we'll see most of the data points on the 0 and the 1, because their labels are like this. And if you see, this is the x1, what do you say, x1 column, x1 axis. This you can think is x-axis, the z-axis, and the y labels are belonged on the y only. So this way, if you see, all the data points mostly falls on the 0 label and 1 on the y side. So you will see all this point. And what we usually do is basically we create a predict function, mostly a straight line with a y-intercept, right? This is just forget few of the things which is just similar like this. This was the predict function which we were using previously. To straight line with the y-intercept, and the straight line, the slope will be this theta. Basically theta 0 is basically the slope part, and theta 1 you could think as y-intercept. But this, and forget, just for now, just forget the sigmoid function and this definition over here. And I will tell you why I'm telling you to forget that, because this straight line in no hell is gonna match it. Whatever value I find for theta 0 and theta 1, never gonna match it, and never gonna match it, never gonna fit over here. So we have to come up with another line. And one of the reason why previously when we were doing linear regression, it was called linear, because the line which we were fitting to fit all the data points was mostly a linear line. Linear line is basically straight line with, we will have see this function, multiplication, addition, and this kind of thing, theta 1 multiply with x0. But if you see this line, we probably required a curved line, S-shaped, something like this, to fit this thing. So whenever we are dealing with curved things, right, lines where things are curved, or those kind of functions are called non-linear function. That's why this is called not linear regression. This is called logistic regression. not linear, basically logistic. I will tell you why logistic is there. So this is called logistic regression, and there the straight line is not going to help you. Linear functions are not going to help us, right? Those straight lines are called linear function because everything like goes linearly. You may have to research a bit on linear and non-linear, but I pretty much explained you on that. So we need a function which is curved, and that's why we have a called sigmoid function, which will help us to curve the straight line kind of S shape so that it fits on it, and we'll see how that's looks like. So we probably will have same theta1 and theta2 random values, and one of them will act as a slope. So in this case we don't have a slope but basically a S-shaped curve. So how big that curve should be. So over here the first theta value is deciding how the curve will look like. So bigger number will have more curve like this feature, and once I have like good enough curve, that time I'll stop and then I'll try to fit in the other part. This is very similar to y-intercept, but over here instead of you can think of as an x-intercept, or yeah, it's kind of x and y-intercept. Basically it is over here and I have to bring it somewhere here. So this intercept, like if I just reduce this value from here, it will go somewhere where actually it fits. So around, I think it will be 5 or somewhere near to 5. So at 20, yeah. So at this point, you see, we will have our curve like this, right? So now instead of straight line function probably will look like a straight line, this not exactly like an intercept or something like this. And when we do that, I'll have my sigmoid function make it look like curve, and then it fits like this. So basically our goal will be to find these golden words. Over here we randomly did it. This is not the way on the screen we do it, right? This is not how we do it. We have a mathematical model where we don't have to do graphs and all to do that. We will probably do it just simply using math, and we have to find these golden theta1 and theta2 values, right? So that's how we will roll in this video. So, and again same, the loss function, loss will decide how well my line is fitting, right? So that is basically similar to linear regression. Whatever the prediction value over here, you can think prediction value I'm using as p, and I'm using the sigmoid inside this prediction function, and whatever the prediction, whatever I get, I'll do that. I'll sum those losses, right? Square we usually do to remove the negation, and so the total loss function, basically this loss function takes the input. It takes a lot of things, x1, x2, x0. Just in this to simplify, we say that loss function only take theta1, theta2, and if we just pass on theta1, we will have a loss function, and we have 8 examples, so we are just averaging all of them, right? So that is how a loss function will look like. And you might think that that loss function would be good, but that loss function, if I plot that loss function, you already know how we plot data, right? That loss function, if I just pass all the random 01, 02, 03, all the theta values, I can just plot those dot points and just make a loss function like this. And this loss function will not work, because what happens is that when you plot that loss function, you will see this loss function has a straight curve over here, flat path over here, and this is a zoomed out version of loss function. But if you extrapolate that for a bigger theta1 and theta2 value, then you will see a lot more curves, like, and that time finding the lowest point become very hard. And if, let's say randomly, if I start my theta value from somewhere over here, what happens, the slope is already 0 over here, right? When the slope is 0, then the formula is like theta1, theta1, so this slope becomes 0, and 0 minus theta1 and 0 minus theta2, it will not change, and it will just be over here, it will just jump around here over here, and that is not a good solution, because some solution lies somewhere over here. So whatever, because of that, we made sure that our prediction function was good, but our loss function is not justifying things what we intended with linear regression back then. Similarly, we are trying to intend over there, it will work the same way, but this will not work like that. And if you just try to reduce this theta with that loss function we had, and we could as we have learned from our previous formulas, that we'll find the derivative of that loss function with respect to theta 1 and theta 2, as you can see over here. And so if it will just jump around here and never it will converge to the lower value. So the previous loss function which we learned was not good enough. So we probably had to change, just like we changed something in prediction, we have to do some kind of change in loss function, which I'll tell you. So this was the loss function which we learned previously, right? A simple one, modulus, square, whatever you feel like. Yeah, square for just to negate the negative numbers. And so this loss function will probably not work. So the another loss which we required is we call it log loss, and the log loss is quite similar with the previous lot. Instead of this, this y hat, if you see, is basically the predict function, basically the sigmoid x1 x2. This part is basically y hat, and this log loss, you might be afraid. When I saw this, when I was studying about this thing, when I saw it, I got afraid. What is this big equation, right? I used to have math phobia back then, so I was so afraid what this log loss is. And if you don't even understand it first go, it's completely okay. I'm gonna expand that. Even if you don't understand, that's totally fine. Just give it some time. Just use the pen and paper, solve that. You'll probably understand. So what this log loss is basically telling, it's like conditional. So if it is when your y value is actual label over here. When the actual label is 1, the loss value, this loss thing, right? This loss, right? This loss will be basically minus log whatever the prediction I have, and this prediction comes a sigmoid function. So let's say my prediction was 0.8 or something like this. So then the loss for that example will be, right? That for one set, that example will be like 0.8, whatever the log value of 0.8 in the subsection. Whatever that value comes, that will become logs, and that is for only one example. You have to do all 8 examples like this, and you sum them up, like that is the summation over here, and if you sum them, you will probably get it. So this is for all the example which has 1 as a label. So that will be, I think, only 4 of them, right? 3 of them, sorry. So 3 of them, I know what is the loss for 3 of them. What will be the loss for other 3? So other 3 will be like basically when the actual labels are 0, and then this 1 minus whatever my value was. Let's say my prediction was like 1 minus 1 whatever the prediction y had was. So let's say the prediction was 0.2, something like this. So 1 minus it becomes 0.8 and minus log whatever the result is, right? So what is doing is that this log is basically what is after minus 1. It is making sure that, so it is making sure that all the loss, so let's say my label was 1 and I got the prediction 0.8. So only 0.2 difference is there, right? So the loss will be log 0.2 only, right? Same way, if my label is 0 and my result is 0.2, I'm only 0.2 apart. And same way, when the y was 1, I was only 0.2 apart. Like in both scenarios, we were only 0.2 apart from the actual label, right? Think of an example for y1. I'm repeating again, maybe I was a little fast. Think of an example where the prediction was 0.1 when the label was 1, actual label 1, and when the label was 0, actual label was 0, I had 0.2 as a solution, right? In both cases, prediction are different. In this one it will be 0.2, and this one it will be 0.8. But if I just 0.8, if I'll input, I'll get a loss function, and if I just put 0.2 for this example, I will only get 0.8. So we are basically making it equal, even if the class is 0 or 1, so that whenever it goes into log, it becomes equal number from the both end. If I'm far away from 0, 0.2 or 0.3 distance away, same way if I'm just from y label 1, I'm apart only 0.2 or 3, basically that will be 0.8 or 7, something like this. So just making sure that I have equivalent amount of loss in both scenarios, 1 actual label or 0 actual label. So that's why this log loss makes sense, because it equalizes thing, although even though we have different, their distance, like what we say, the divergence from their actual label, we are trying to make it equal. And so just ignore this 3 explanation part. and we will have our updated logs. Just remove all this initial 4 lines. Our updated log loss will be a summation of all these example. If they are 0, then this one. If they are if the actual labels are 1, then use this part. If the actual labels are 0, then use this part. So this is, you can see 1 minus 0, right? If it is a 1, if the actual label is 1, then 1 minus 1 becomes 0 and 0 will multiply. So this will cancel away. So this is basically combining these two if condition into a form of equation by having this bracket over here and adding this thing. So whenever the actual label is 1, this 1 become cancel, and this part will get cancelled. Whenever there is 0, so if you apply 0 over here, then this will get cancelled, right? So above 1. So this is such a beautiful use of math, smart math, which we have done over here, and we'll have our loss function. And what is the beautiful part about this log function? We can probably do an example over, just take a run how it looks like. So let's say we have this example when x is 1 and x2 is 6, right? x1 is 1 and x2 is 6, and the y label is 1 for this example. I think we are talking about, yeah, this one, this row. So if we apply this thing, and let's say how the prediction will look like. So the prediction function over here, I think we'll probably choose some random theta value, right? So 0.2 and 0.5 as the theta value we have chosen randomly, and if I solve, I'll probably get this 0.69, something like this. Just a second. So this value will get, and if I solve it, I'll get 0.04, right? So for some prediction where I was only 0.96 and the log values, I'll get 0.4. Let's say another example where the prediction was something like this, 0.011, right? In that case, if you see the log, what helps is I'll get some value like 0.12. So if you see, they both are very, so this one is very, let's say the actual label was 1, and so if you see, it is a quite true, the solution. If I see, if my actual label is 1 and I am getting the value 0.96, this is very good prediction, I would say. And the good prediction, what we do is that I'm getting, so we don't have to have very high loss. So the loss, you can see, is 0.0 only, 0.04, very little loss. We don't have to change much, thetas are already perfect. But think of an opposite example, just instead of 0.96, opposite toward the 0 class, same number but on the opposite side of the 0 class, I'm bad, right? And if I just has to penalize, think of an example, think of our previous loss function, this is the value, right? So that time the loss is pretty little, 0.1, even if I had a wrong prediction, right? This example was, actual label was 1, but our prediction, think of example, our prediction was 0.1 only. So that time, what I would say, that time, although it is a very bad prediction, but the loss is also very little, 0.1, which doesn't make sense. But if you just pass with log, I get a better loss when you are actually doing some wrong prediction. So that time the loss will be bigger, and this will help us to optimize our way better than what we intended. So that's why log helps a lot over here. That's why we call it also logistic regression. So I hope you understand that. Sorry. Okay. So this was it. So this is the loss function, and when we plot that loss function, it looks like our linear one, very simple curve, whatever the points are. And if we just optimize theta with our this method, I'll explain more how we got this part, how we get the derivative over there to help to reduce our theta values. And if I do, at some point I will edit the best theta where the losses are minimum. So somewhere over here, right, that will reach. This we have learned in the linear regression as well. So yeah. So now you understood why we use this sigmoid function, because the straight line will not fit. Why we use log loss function, because log helps you to have equal penalization. Whenever you have, like, whenever the classes change, you have equal penalization. And also we have seen the log loss, what do we call, uh, when we extrapolate log loss on a graph, right? We see the previous version of simple, we call it mean square error loss, that one before the log one, that has so many curves up and down and flat surfaces, which is not for good for optimization. But when we convert into log loss, we have this very simple curve where we can actually optimize it. Correct? So that was my understanding. That is actually true understanding. If somebody else have a better understanding, do let us know in comments. So that's how we do there over there. And now some example. Let's say my theta ones are 0 0 and my x1 feature is 1, x2 is 6, something like this. I'll do some prediction over here. I'll get the values over here. Prediction 0.5, log loss was 0.69, right? If I change the theta, same, the loss will change, y prediction will change. So this is how we will do it. And our goal is to find this theta value. Like, this is the random way, but we can probably use gradient descent method to understand how this theta will work. So let's deep dive on the log loss. And if we just extrapolate the log loss over, instead of y hat, I'll just write those prediction function. This is the symbol for sigmoid, which people usually generally use it. I think it's called mu or sigma, I guess. Yeah, sigma. So this is for sigmoid, and we can write something like this. And how we can find out those best theta, that we already understood. We can probably find the differentiation of log loss with respect to theta 1, which will basically tell me the slope at that theta, like at that curve, right? You see that curve, right? On that curve, where if I am on the, if goal is to go the loss where the curve is 0, so where this bell shape thing over there, the loss is 0. And if this, I think you already understand, right? Whenever it is a very high slope, just make sure you subtract your theta. Whenever it is little on the other side, you subtract it. The goal is to reach where the theta, the slopes are 0. So that's why we will probably find differentiation of log loss with respect to that theta. And what is the funny part is, coincidentally, if I solve it, if you solve this big loss function with respect to theta 1, you will find the same thing, same result what we find in the linear regression. Basically, prediction minus actual level multiply by the x feature, right, in that example. So we have 8 example, right? So just find whatever the sum is of that example and sum them. For, like, for first example, you'll do it, whatever the prediction you'll get, subtract it, and whatever the x feature was there, you multiply with that, right? And you just do it, and you will probably, and just optimize the theta this way. I will probably explain you in the next slide how we got this thing, how when we do the differential log loss with respect to theta 1, and then this one case of theta 2, how we get does the same thing. So that probably we're going to do in the next slide. So here the dummy is 0.5 in theta 1, and if I just play with the number and this theta value, you can see different logs coming out, and here are the few calculations. So you can see the theta is decreasing, and the values at some point we'll probably find a good solution around 0.5 and 0. Even though when you start with negative numbers, right, negative numbers is basically on the other side of the graph, and again you just multiply and do the calculation. You will, again, I will reach back to the same theta's 0.2 and 0.1 values. So that will be, when we save this, that will become the model point, right? That is the golden weights, where I have the least loss for each example, and the line is completely fitting that dotted line. If you see, instead of straight line, we'll have this curve. This will exactly fit like that, and I will have a model. And in the future, if I get new x1 and x2 features, I'm gonna probably predict what class it will be. So that's how we'll do. Next slide, I'm going to tell you how we have how this thing comes, prediction minus actual label into multiply by the feature. So log loss. So this is a prediction function over here with sigmoid and all. Log loss looks something like this. So if I have to find theta 1 respect to the loss. Because one way, so there are two ways to do it. One is the systematic way, other is the simple way which we have done in our high school, like basically how we do the differentiation. So just replace this y hat with this whole thing, sigmoid z, and z replace the z with 0.c. So instead of y it will be sigmoid bracket 1 upon 1 plus e to the power negative, on the z part it will be theta 0 x0 plus theta 0 x1, big chunk, like it will be very heavy, and then you do the differentiation and you follow the channel, because there are so many functions inside the function, you follow the chain rule. So that is one way, simple way, which I actually like, because that's way how I done in the middle school or high school, something like that. But the systematic way is to do chain rule, and you can write finding a derivative of loss function with respect to theta 1, whatever the theta 1 to j. We can break into multiple part. What we can do, we can find the derivative with respect to only the y hat, right? The simple y hat. Just this equation, find the derivative with don't think the loss function is built from y hat. Just don't think that y hat is another function. Just think y hat is a variable. Find derivative of that. So if you find the derivative of that thing with respect to y, loss function. So y, so if you see, I will write y like this, and derivative of log y is basically 1 upon y. So you can see minus y upon y. So this minus will get multiplied over here. So you'll get this value. If you come to this part, 1 minus y remains the same way. Log become, chain rule will, like basically log will become 1 upon 1 minus y, that is over here, and the plus sign will be. So this is the how the y part. Now we will probably differentiate this function. So now differentiation of prediction function with respect to z. So z is on somewhere over here on the exponentials. So exponentials are basically, so if you solve this, will be little complex. You can use pen and paper to solve this. If you solve this thing, or maybe you can use ChatGPT, you'll get y hat minus 1 minus y, right? And in the last, if I do the differentiation of this z function with respect to theta, so this theta will be x, and x0 will I will get, because the theta, for theta 0 it will be x0, because this will become a variable constant, so that constant will be there. And then again for theta 1 it will be x1, right? That will be also constant over there. And if I just combine all of my result, like this result multiply this result and this result, I'll probably get prediction minus actual label, y hat minus y. And the theta for, like this is for theta, like basically this is which we initially wanted, a differentiation of loss function with respect to theta 0, that will become y prediction minus actual label x feature multiplied by x feature. Same way the theta 2 prediction minus actual with the feature of which is multiplied with theta 1, so that will be x1. So this way if we'll do, we'll get the same result what we got with linear regression, right? The derivatives part, and we can use this value to subtract those theta or addition those theta in a loop, and theta will somewhere get automatically that we have seen is that, yeah. So this is basically theta 1 theta 2, so you will just merge somewhere. And these value, you know, this is prediction minus actual label multiplied by x feature. This will be prediction minus the x1 feature. So that we have done. I think you probably understood that step. And let's say, imagine, well, while doing it, we got our golden result. So now you have to forget everything. So this is the training part. So when we actually code and everything, you can do the training part, everything, and just while saving, when you're actually using the model into production, you just have to delete everything. Just have to keep this theta function and our predict function. The theta value, not theta function, but basically the theta values, weights. And this is the theta weight golden weights which we have, where all the example values, like all the 8 points fits really well. And this has a lot of information inside these two values. And we'll use example where x1 is 1, x2 is 15. And when we do the prediction, basically multiply each other and do the summation and then put it in a sigmoid function. And we'll do that. I'll get a prediction of is around 0.35. So whenever you got this point, so one last step we have to do is whenever you get these values, right, like this, So this looks very, so we have to put a point, like if something is 0.5 below, so you will never get actual 0 and 1. So when the prediction comes, you will never get 0 exactly 1 and something like this. It will always somewhere near, right? Near. So it will might have 0.1 or 0.9 or something like. In that case, anything is above 0.5, you can call it to a 0 class. Anything above 0.5, you can call it the 1 class. So in this case, we have 0.35, which is below 0.5. So we call this class belong. It is more nearer to class 0. So that was our prediction. So that was the end of how logistic regression work or a classification work. Why this is logistic? Because we have changed the prediction function. It's not linear anymore. We have added sigmoid, which is a non-linear function over here, which help you to give this curve around us while fitting the model, and log because logistic regression, because we are using logs in the loss function, because normal loss function doesn't do well. So that's the full story. I hope you got a lot of value. Even if you're stuck, I think you might have to give another view to this video or something like this. So when I was reading it the first time, I had to go through multiple videos of different people at different time. I would stuck somewhere, and again I will try after 2-3 days again and again. So within like 2-3 weeks or something, in the end I will be able to understand. Even though when I understood it, in the job I was using a lot of built-in libraries, so I don't have to go through these things. So even though I understood it, after some I forgot all those things because I was not explaining to anybody or not using it in my daily life. But when I started teaching, like again with many iteration, I'm now at a very good place where I can understand this. So similarly with you guys, you might on the first go understand 50% or 60% certainly. In the next iteration you might understand 60 or 70%, and then usually it goes, and you have to give multiple repetition after a year or 5 months or 6 months after 2 years, and then somewhere after 2-3 years you will I got like 100%. But yeah, just to work around, do some job, I think you will be good to go in the first attempt only, right? Just 60% you understand, I think you'll be very good to go. So this is it. I'll probably have codes, but I don't know how to share it and everything. But yeah, do let me know if you needed the code for this section, just for practice. Okay, so that's it. Let me see if I have anything else. No. So that was the example. Maybe, yeah, I guess I don't have much. So that is for today, guys. I hope you have understood it. Let's see each other in the next part of this third season. What I will be telling you, I will telling you how to do multi-class, basically not only 2 classes or 3 classes. Maybe I'll tell you what is feature engineering, something like this in the next one. So I hope you are there with that for that thing. I'm very excited to show you how that is work, and eventually lead you to neural network, how you'll understand neural network work. So